All right, this is question 1 on Unit 8. An object possessing an excess of 6.0 times 10 to the 6 electrons has what net charge? Recall from the preceding facts that the elementary charge is 1.6 times 10 to the negative 19th coulombs. Now, College Board wants you to refute any claims that a charge less than the elementary charge has ever been isolated. So recall from our discussions that this is the smallest charge that an electron or proton can have, and charges occur in discrete units of the elementary charge. Okay, so we have 6.0 times 10 to the 6 electrons, and you're being asked what is the charge. So we will simply multiply that number of electrons by the charge of one electron to get our answer. Note that it is a negative sign because we're dealing with negatively charged subatomic particles. So the answer, negative 9.6 times 10 to the negative 13th coulombs. Now, on a side note, you may recall from your studies of chemistry that this charge was first isolated and discovered by Robert Millikan in his oil drops experiments. Question 2, we have an alpha particle and it has 2 protons and 2 neutrons. What is the charge of an alpha particle? So we know that the neutrons carry no charge, so this question is basically saying, what is the charge of 2 protons? Well, that's going to be 2 times the elementary charge, which gives you 3.2 times 10 to the negative 19th coulombs, and that is a positive value because we're dealing with protons. In question 3, what is the net electrical charge on a magnesium ion that is formed when a neutral magnesium atom loses 2 electrons? So it's lost 2 electrons, and so we have a magnesium cation in this case. So what is the charge of each electron that goes away or is lost or is given away or transferred? That would be 1.6 times 10 to the negative 19th coulombs. So all you're going to do here in this case is multiply the elementary charge by 2, and that'll give you an answer of positive 3.2 times 10 to the negative 19th coulombs. And that is because those electrons are given away or transferred, and that leaves an overall charge of positive 3.2 times 10 to the negative 19th because we started with a neutral magnesium atom. Question 4 here. We have a neutrally charged glass rod and a neutral silk cloth. When the student rubs the silk cloth onto the glass rod, the rod acquires a net positive charge of 45 microcoulombs. Part A, what is the charge on the silk cloth after the student performs this experiment? Now, I have a schematic here. The schematic is not dealing with a glass rod. It is dealing with a piece of amber, but it's a good visual representation of what's occurring in question 4. So let's go ahead and look at the amber and the piece of cloth. They're both net charge of 0, just as in question 4. And when they are rubbed together, we see the piece of amber now has 2 additional electrons on it. So where did those electrons come from? Well, recall from the conservation of charge that they, charge is not created, it's not destroyed, it is conserved. So it came from the cloth, it came from the piece of cloth, and that left behind the protons on the cloth, which means the cloth now has a net positive charge. The piece of amber now has a net negative charge, but together, zero, neutral. So that original charge of zero in those two neutral pieces is conserved. What did we start with? Overall nets zero. And even though the amber now has -2 because it has two subatomic particles, each carrying a magnitude of charge for the elementary charge, it has now left behind on the cloth three positively charged, so 3 protons and only 1 electron. That gives a net of +2, net of -2. Those cancel, giving 0. Okay, enough of that. Let's look at the problem here. So what has happened here is that the silk cloth has taken electrons from the glass rod. And then everyone that leaves the glass rod, as I just got done explaining, leaves behind a proton that was used to balance the negative charge of the electron. Now, let's find out how many electrons were transferred. Okay, so we had 45 microcoulombs. Well, recall that there are 1 million microcoulombs in 1 coulomb. So using dimensional analysis, we can go ahead and get that converted over into coulombs. And the next piece would be to understand in 1 coulomb, there are 6.25 times 10 to the 8th elementary charges or particles or electrons or protons, whatever you were dealing with. So that is also laid out on the problem set in one of the facts. And if we look at our units here, we end up with electrons, which are the elementary charge. And for 1 elementary charge is 1 electron. That last step, not 100% necessary by any means, but in these videos, I want to give you a thorough explanation. And that leaves you with an answer of 2.8 times 10 to the 14th electrons. Question 5. 3 protons are separated from a single electron by a distance of 1 times 10 to the -6 meters. Find the electrostatic force between them. And is that force attractive or repulsive? All right. College Board will ask you questions comparing the electrostatic force with the force of gravity. And so you need to understand that the electrostatic force can be either a positive or negative. So it can be either a repulsive or an attractive force. So here we have 3 protons and they are separated from an electron. So that in itself, you should see, well, from chemistry that that's an attractive force, that those are going to come together. So in this problem, we should end up with a negative sign in our answer. All right, this is our first problem where we're dealing with Coulomb's law. This was named after a French physicist, Charles Auguste de Coulomb, and this is his law, and it is an example of an inverse square law, which we'll talk about in some of the upcoming problems. Let's figure out the answer to this particular problem. Using Coulomb's law, we can calculate the electrostatic force. We have here 3 protons, and they're separated by a given distance by an electron. So in this little schematic here, I'm representing that we have these 3 positive elementary charges, which we know to be protons. And on the right side, we have 1 elementary particle with a negative charge, and that's 1 electron. Okay, so now we can start to put in numbers. We have the constant for Coulomb's law. We have a total of 3 positively charged elementary particles, each carrying a charge of positive 1.6 times 10 to the negative 19th. Then we have our electron. There's only one of them, and it has a charge of a negative 1.6 times 10 to the negative 19th coulombs. And that quantity is going to be divided by the distance between their centers squared. Okay, so using your calculator, be careful how you put this in so that the calculator does not misconstrue the order of operations. We've talked about that extensively throughout the course. So the electrostatic force can be calculated to be negative 6.9 times 10 to the negative 16th, and that is in units of newtons. And you can look at your units here, as I've asked you throughout the course, and looking at your units and the units for the Coulomb's law constant, you end with units of newtons. So this confirms our prediction that we should end up with negative signage, that this is going to be an attractive force between those two particles. In question 6, a beam of electrons is directed into an electric field between 2 oppositely charged parallel plates. So we know electrons to be negatively charged subatomic particles, each electron carrying the negative 1.6 times 10 to the negative 19th coulombs, which is the elementary charge. So we have our diagram. In which direction is the electrostatic force exerted on the beam? Well, we know that the negative particle is going to be attracted to the positive side, and it's going to be repelled from the negative side. So that should be very intuitive for you at this point, especially given your studies of chemistry. So the force would be exerted toward the top of the plate for that simple fact alone. In question 7, consider these 2 small spheres, one carrying a charge of 1.5 nanocoulombs and the other carrying a charge of a negative 2.0 nanocoulombs. They're separated by a distance of 1.5 centimeters. Find the electrostatic force between them, and lastly, describe their interaction. So we're going to be using Coulomb's law again here to solve this problem. And so let's go ahead and get some of these variables converted over. Coulomb's law, we need to get nanocoulombs into coulombs. So recall that there are 1 billion nanocoulombs in 1 coulomb, so we can use dimensional analysis to convert both of these values over into coulombs so that we're using the units that are SI units, and we're going to be also obviously putting in a distance in meters when we go ahead and square that in the denominator of the Coulomb's law equation. Okay, we have our signage represented, making a prediction of how they would interact. Well, we're going to get a negative electrostatic force, and that is representative of an attractive force. Okay, now recall in our studies of the universal law of gravitation that the force of gravity gives you, that's an attractive force, whereas Coulomb's law can be either a repulsive or attractive force. So our answer, negative 1.2 times 10 to the negative 14th newtons, all right, or excuse me, times 10 to the negative 4 newtons. So we have a negative sign, which is indicative of an attractive force. So these 2 particles, or spheres rather, are going to be coming together, okay? So when they come together, that is going to be, they're going to move straight towards each other, all right? And you can see this being represented here in this animation. So not only have we calculated the electrostatic force, but now we've been able to describe their interaction with one another. In question 8, two charges are separated by a distance a, and we're given a diagram. Part A of the question: which is greater, the force of Q positive on the positive 2Q, or the force of the positive 2Q on the positive Q charge? So that's what you're being asked to determine. College Board will ask you this question. They want you to understand that these two subatomic particles are going to exhibit Newton's third law. They are an example of a Newton's third law force pair. So the particles will exert equal and opposite, so equal in magnitude, opposite in direction, on each other, and are a classic Newton's third law force pair. All right, the next part of this question: in terms of the given variables and the fundamental constants, determine the magnitude and direction of the force of the positive 2Q charge on the positive Q charge. Okay, so this is a very simple derivation using Coulomb's law. We're simply going to be putting in the variables we're given here. We're not worried about numbers. So the fundamental constant in this case is K, the Coulomb's law constant, and we have our charges indicated, and we have our distance, which is given as A. That is in the denominator, and that is squared. You could have simplified this to 2Q squared over A squared. Either way is fine. So a positive electrostatic force, what does that indicate? A repulsive force. So the particles will repel one another. All right. In part C, by what factor would the force calculated in B change if the distance between the charges was now increased to 3A? So it's 3 times greater the distance. This will also be assessed on the AP exam. This is an example of the inverse square law. So when you look at Coulomb's law and you look at the equation, that distance is in the denominator and it is squared. So if we were to say that this force is proportional to the inverse of the distance squared, that would be accurate. And so if we put in numbers here, we have that the electrostatic force is proportional to 1 over 3, but that 3 is squared. So what is that saying? It's saying the distance is 3 times greater. Well, 3 squared is 9, so our electrostatic force goes down 9 times. It's 9 times less the force that it was when at distance A. All right. So in the next part of this question, we're going to answer part D and look at if the positive Q charge was now replaced with a negative Q. So we're going back to the original scenario of a distance A. Describe how the magnitude and direction of the force between these will change from the original situation. Well, it's fairly obvious that now we will get a negative electrostatic force. And the electrostatic force carrying a sign of a negative is an attractive force. Okay, so the particles will come toward one another. However, they will have the same magnitude of force. In other words, the amount of newtons is going to be the same. It's just in an opposite direction. And in this case, that minus sign means that those are going to come together, but with the exact same magnitude of force. Question 9. The centers of two small particles are separated by a distance of 1.2 times 10 to the negative 4 meters. The charges are given in coulombs for each particle. And in part A, you're asked to calculate the magnitude of the electrostatic force between those two particles. Okay, so here we have Coulomb's law and the equation. We have K to be Coulomb's constant. With the units, we have Q1 equal to a positive charge. We have Q2 equal to a positive charge. And we have that distance in meters squared. So we can make a prediction that this will give us a positive value for the electrostatic force, and thus the force will be repulsive. Let's go ahead and get an answer here. As always, be careful entering this into your calculator so it does not misconstrue the order of operations, and we get a positive 2.4 times 10 to the negative 19th newtons. So it's inversely proportional to the square of the distance. As you know from the last couple problems, it's an example of the inverse square law, as you now know from the last couple problems. So the electrostatic force is directly proportional to the inverse of the distances and can be represented as shown here. Graphically, we have on the y-axis the magnitude of the electrostatic force. So we're not worried about the signage, the magnitude of the electrostatic force on this particular graph. And then we have the distance between the centers of them. If we graph this, this graph is indicative of an inverse relationship, and in this case, an inverse squared relationship. So recall, if you wanted to linearize this graph, you would need to take each data point on the x-axis. You would need to square it, and then you would need to take the inverse of it. Once you did that, you would end up with a straight line linear regression that would have a positive constant slope. All right, question 10. Consider 4 equal positive point charges that are situated at the vertices of a square. Find the net electric force on a negative point charge that is in the square's center. And so you have a schematic on your problem set here. And just a reminder from your College Board big ideas that the total amount of charge in a system is equal. You're going to need to be aware of that. You're going to need to understand equal amounts of positive and negative charges can cancel each other out and can be neutral, but they are still there. They still exist. Charges can be transferred, but the total amount is constant, and we've shown that in a couple problems, specifically with the silk cloth and the glass rod. Also remember that the elementary charge is the smallest charge, and any charges must be in units of that elementary charge. All right, let's get to the problem here. So we have the negative particle in the center, and then we have these 4 positive charges that are situated at the vertices of the square. So let's go ahead and use an orthogonal approach for this problem, and let's use some trigonometry rather to analyze one charge interaction, and from that we can sum the forces and answer this problem. So if we use vector addition here, we have our force 1, the vertical component of force 1. We have the horizontal component of force 1. And we have the overall resultant vector, okay? And in this case here, that vector is pointing this way, all right? So let's look at the trigonometry here. And using vector addition and force, summing the forces here, we can show, if you did this for all 4 areas, well, you have 2 positive in the y directions. Okay, so F sub 1 vertically, F sub 2 vertically, and since they're both 45, we can simply add those together and say that it is 2 times the force multiplied by the sine of 45 degrees. And going back to our, our diagram here for this particular one, which was this triangle over here, you can see if we're looking to solve for that vertical component, it is opposite of our angle theta, 45 degrees. So we can say, we can use a sine function here, and it's 2 times that because everything else is identical for these charges. Okay, now look at charge 3 and 4. We'll see those charges, as I'm sure you can see, are going to have a down, and this guy is going to have a leftward, and F4 will have a rightward. So if we stick to convention here, and we'll just sit down negative, up positive, left negative, right positive. So we could call F sub 3 vertical plus F sub 4 vertical. Those are negatives. So we end up with a negative 2F sine 45 degrees. So the magnitude is the same, and the directions are opposite. So that means that the forces will completely cancel out and be 0. Now let's look at the left and right. Okay, we'll do the same thing, except on this time we have forces 1 and 3 and forces 2 and 4. So forces 2 and 4 are to the right, so they're positive. Forces 1 and 3 have a leftward component, so they are both negative. All right, and that's force 1. And so we can clearly see, based on the trigonometry here, that those are going to cancel left and right. So up and down cancel, left and right cancel. They completely cancel each other out. Okay, so in that part of question 10, there was no, it stayed in the center because all of the forces canceled out. We showed that using vector addition and trigonometry. However, in question 11, you're looking at those charges on the bottom. They're not there anymore. And how is that going to affect the net electrostatic force on the negative charge? Well, here we have our triangle. So we can look at this orthogonally again, and we can use vector addition again, which you used in question 10. And so let's go ahead and see what's happening left and right in the x or horizontal directions. Well, the force 1, that has a leftward direction. We call left negative and right positive. Force 2 has a rightward direction. And so when we add those up, we get 0 newtons in the x direction. So there's no force acting horizontally on this system. However, if we look vertically now and analyze these, we see that both of these have that upward or positive force. So we get an answer of 2 times the force multiplied by sine 45 degrees. So we're going to have this negative charge is going to move straight upward, and the charges are opposite, and we know that's an attractive electrostatic force. Okay, so they're going to move, the one particle is going to move straight up toward the centers of the positive particle 1 and positive particle 2, and that is going to be with a 2F sine 45 degrees. Okay, in question 12, a charge of 30 coulombs passes through a 24 ohm resistor in 6 seconds. What is the current through the resistor? So some of the preceding facts on the problem set. Current is the charge divided by the time. So it's that rate. our units are going to be amperes equal to coulombs divided by seconds. Those are the SI units here. Okay, so let's look at what information we have. We have our charge, Q is 30 coulombs. We have a 24 ohm resistor, and then we're being told the amount of time it takes for those coulombs to pass. Well, this is a very straightforward calculation then. We're going to take 30 coulombs divided by 6, and the answer is 5.0 amps. Question 13, a charge is flowing at a rate of 2.50 times 10 to the 16th elementary charges per second. What is the current? All right, so recall the magnitude of charge for an elementary particle is 1.6 times 10 to the negative 19th coulombs. So with that information in mind, how many, well, we have 2.5 times 10 to the 16th of these elementary charges, and that's our starting point, okay? And using some dimensional analysis here, we can say, well, each elementary particle has a magnitude of charge of 1.6 times 10 to the negative 19th coulombs, which means we have an overall current, or excuse me, charge of 4.0 times 10 to the negative third coulombs. All right, what is current? Well, it's charge divided by time. It's a rate. Okay, well, we just calculated the charge by taking that amount of elementary particles and converting it into charge, into coulombs, and we're also given information where we can say, well, it's at a rate per second. So the answer, therefore, is our charge divided by 1 second. So our final answer is the current is going to be 4.0 times 10 to the negative third coulombs over second. Well, coulombs over second, amperes. So amps would be our units here. In question 14, the current through a light bulb is 2.0 amperes. How many coulombs of electric charge pass through the light bulb in 1 minute? 1 minute is 60 seconds. We need to stick with our SI units. So coulombs divided by second is an ampere. Okay, and we have information here. We have the current. So we're given the current through the light bulb to be 2.0, and that must be equal to the charge divided by the time in seconds. Rearranging this, we can solve for the charge to be 120 coulombs. Okay, algebraically multiply both sides by 60 seconds. Boom, we're done. 120 coulombs is the current, or excuse me, is how many coulombs pass through the light bulb in 1 minute or 60 seconds. In question 15, the current traveling from the cathode to the screen in a television picture tube is 5.0 times 10 to the negative fifth amps. How many electrons are striking the screen in 5 seconds? Okay, so what are we given here? We're given time, we're given amps, and we know the magnitude of charge for each elementary particle is 1.6 times 10 to the negative 19th coulombs. That is the smallest unit of charge. There's nothing smaller. And we have here the equation for current. Current is charge over time, so coulombs per second. And we're being told the current, which means we can set that equal to the Q, which is the charge, divided by the time, which we're told asked in a 5-second period of time. And we can rearrange this algebraically, multiply both sides by 5 to get an answer of 2.5 times 10 to the negative fourth coulombs. That is how many electrons, or excuse me, that is the overall charge. How many electrons, we need to go one step further. So now that we know that one elementary particle has a charge of 1.6 times 10 to the negative 19th coulombs, and now we've used the information in the problem to calculate the amount of charge that is occurring within 5 seconds, we can simply convert this over using dimensional analysis, and we get E, which is the symbol for the elementary charge, and an elementary particle. We have 1.6 times 10 to the 15th electrons are striking the screen in 5 seconds. So that's going to be our final answer for question 15. In question 16, we have a 3.50 meter length of wire with a cross-sectional area of 3.14 times 10 to the negative 6 meters squared at 20 degrees Celsius. All right. And we're being given the resistance of 0.0625 ohms and asked to solve for the resistivity of the wire. Here's a nice schematic to go along with the ones that are on your problem set, and the preceding facts about resistivity come from your problem set. So this is a straight application of that, where we're going to solve for resistivity. Looking at the schematic here, we have, the Greek symbol rho is equal to resistivity. We have the length here. We have the cross-sectional area of the wire. We have our equation that resistance is equal to resistivity multiplied by the length, that quantity divided by the cross-sectional area, and that's going to give us the resistance. So let's go ahead and solve this problem. Let's rearrange algebraically for resistivity. So we're going to isolate the resistivity and basically multiply both sides by the reciprocal of L over A. So we get A over L. And we have algebraically rearranged it now for resistivity. And we have everything else that we need. So this is a plug and chug at this point. We have our cross-sectional area. We have our resistance. We have our length of wire. And so we can solve and get an answer here of 5.6 times 10 to the negative 8th ohm meters. Okay. And again, if College Board asks you any questions about resistivity, they will also typically ask you, make sure that you understand that it depends solely on the material. It is a property of the material. Also, you're going to note in these problems that you're going to be given the temperature. So many of our values for resistivity and resistance are calculated either at 20 degrees Celsius or 25 degrees Celsius. So there is a dependence on temperature. So a lot of the textbook values for resistivity, for example, are for a definite temperature, either 20 or 25 degrees Celsius. Okay, question 17. A length of copper wire and a 1 meter length of silver wire have the same cross-sectional area and resistance at 20 degrees Celsius. Now again, note that the temperature is given because there is something called the temperature coefficient of resistance, which is beyond the scope of this course. But resistance and resistivity, these are based on collisional processes, so they are temperature dependent. So you will typically see the temperature. In this course, you're not going to be using the temperature, but I wanted to make you aware of this fact. Okay, so the resistivity of copper is given as such value ohm meters, and then you're given the resistivity for silver. And please remember that the resistivity is dependent on the type of material. Okay, so we have silver and we have copper, and we're asked to calculate the length of the copper wire. So, first and foremost, let's start with what we're given and go from there. So, we have the resistance of silver being equal to, so we've given the resistivity, and we're given the length of 1 meter. And we have our cross-sectional area, which has been left as A because they are constant between both materials. So the silver and the copper both have the same cross-sectional area. So we're going to just leave that as a constant A. Let's do the same now for the resistance of copper. The resistance of copper is equal to the resistivity multiplied by some unknown length, so call it X meters, divided by that same constant A. Well, now we have these two expressions, so we can really just set them equal to one another. And that's exactly the way you want to solve this problem. So setting the resistance of copper equal to the resistance of the silver, and then algebraically you can rearrange this problem to solve for X, okay? And when you do that, solving for X, so in other words, dividing both sides by 1.7 times 10 to the negative 8th ohm meters gives you a length for the copper wire to be 0.924 meters. Question 18. A 10-meter length of copper wire is at 20 degrees Celsius. The radius of the wire is 1.0 times 10 to the negative third meters as shown in the diagram. Calculate the resistance of the wire. Okay, now depending on where you're picking up in these videos, I want to reiterate that you will be given temperature. The use of temperature in any computation is beyond the scope of this course, but the temperature can be used to calculate the temperature of coefficient of resistance. So resistance is dependent on temperature. Okay, so we have a schematic diagram here, and we will use our equation for resistance, relating resistance to resistivity, length, and cross-sectional area. Recall that area is pi r squared, so that's the only little twist on this problem here, is that you're given the radius of the wire, and you'll use that, square it, and multiply by pi to find the cross-sectional area for this copper wire. Also, the resistivity value for copper wire, if you're wondering where that came from, it just came from question 17, where it was given in comparison to copper and silver. So at 20 degrees, that's the accepted value for the resistivity of copper. And we can plug and chug and get an answer for the resistance is being equal to 5.5 times 10 to the negative 2 ohms. All right. Now, moving on to question 19. A wire of radius 1 millimeter and length 2 meters is made of platinum. You're given the resistivity of platinum, and then you're asked if a voltage of 9 volts is applied between the ends of the wire, what will be the resulting current? All right, so let's look at what we're given here. We're given information that basically is going to hopefully lead you to understand you need to consider the resistivity, the length, and the cross-sectional area to calculate resistance. This is also the first problem on the problem set where you're using Ohm's law, where the voltage is equal to the current multiplied by the resistance. So we have everything we need to find the resistance, and so we can plug in our variables for resistivity, length, and cross-sectional area into Ohm's law equation, rearrange for the current, and solve for the current in amperes Please make sure you're entering everything into your calculator using parentheses. Don't forget that you have that cross-sectional area that is squared, and you should get a current that is equal to 141 amps. Question 20. Considering Ohm's law, make a sketch of the graphs for voltage versus current and current versus resistance. If either is nonlinear, how could you linearize the data? What would the slope of the linearized graph represent? We've been doing this throughout the course, and we did it in AP Chemistry as well. So let's take a look at what these graphs would look like for voltage versus current and current versus resistance. Okay, so here, let's take a look at this graph. Here, voltage versus current. We'll look at Ohm's law equation. As the current increases, if resistivity remains constant, what must be happening to the voltage? It must be going up. If the current increases and the resistivity is constant, the voltage increases. If the voltage goes down, the current will go down. So we know these to be a directly proportional relationship. So when we graph this information, we would expect to see a graph with, in this case, as current is increasing, voltage is increasing, a positive constant slope. And if we were to look at what the significance of the slope would be, so that would be change in y over change in x. And our y we have voltage, on our x we have current. What does that equal? Well, that equals the resistance. So the slope of a voltage as a function of current graph is equal to the resistance. So the steeper the slope, the greater the slope, the greater the resistance. And you can see that clearly in this graph of voltage versus current. Now let's take a look at current versus resistance. All right, so if we look at current versus resistance, we know those to be inversely proportional, okay? In other words, as one goes up, the other goes down. So looking at Ohm's law equation here, so as the current increases and voltage remains constant and remains the same, if voltage is constant yet current's increasing, then resistance must be decreasing along that same line of logic. If the current is decreasing and the voltage is constant, well, that must mean resistance is increasing, which would explain why current is decreasing. So inversely proportional, you should recognize the general shape here of this sketch of current as a function of resistance as being inversely proportional. Now, let's look at the significance of the slope, the change in y over change in x. In other words, we have the changing of the change in the current over the changing of the resistance. So what is the significance of the slope? Well, it's not as apparent here because you need to linearize these data. All right. So recall from the graphical analysis handout that was given out at the beginning of the course, is available on PedersenScience.com, and was also given out in AP Chemistry for when we have this overall trend as x increases, y decreases. So an inversely proportional relationship. In order to linearize this data, we're going to take our x data, so all of our data for the resistance, and we are going to take the inverse of that. So 1 divided by each data point for resistance. We're then going to regraph the data. And that, in this case, will linearize these data. So let's go ahead and see what that looks like. It's going to give you a constant positive slope. As you can see here, when we have the current divided by the inverse of the resistance, we get a positive sloping, constant sloped line. What is slope? Change in y over change in x. In other words, the current over the inverse of the resistance. And guess what that equals? Voltage. So on a linearized current versus resistance graph, the slope is equal to the voltage or potential difference. Question 21. An electric iron operating at 120 volts draws 10 amperes of current. How much heat energy is delivered by the iron in 30 seconds? Now, throughout the problem set, there's a few facts and application of questions that are requiring you to distinguish between, like this question says, how much heat energy? Well, energy, that is measured in joules, which by the way was named after James Prescott Joule. So we're going to be solving for joules in this case, and that is to be distinguished from power, which is in watts, which, while I'm at it, named after James Watts, is the rate at which work is done. So we're not being asked what is the rate. We're being asked how much total heat energy, in other words, joules, is delivered by the iron in 30 seconds. Let's look at several of our relationships. Electrical work is equal to charge multiplied by the voltage. All right. Power is the rate at which work is done. So work over time gives us rate. Well, work is Q multiplied by V, or charge multiplied by voltage. Well, this should look familiar here. Charge over time is current. So Q divided by T is equal to I, which is the current. Therefore, work is equal to power multiplied by the time. All right, so we have all these. And in class, you know, I've said you're going to work with rearranging these and deriving very simple expressions using these really throughout this unit. And of course, we have Ohm's law. Voltage is equal to current multiplied by the resistance. So as I've said, this is asking you to solve for energy. In other words, work, units to be joules. And we've gone through a bit of the intuition behind these derivations, these various simple expressions here. Work is equal to power multiplied by time, and power is equal to current multiplied by voltage. Therefore, work is equal to the current multiplied by the voltage multiplied by the time. All right, so if power equals IV, and work equals PT, then work also equals IVT. So take a minute and think about that. Once you get over that conceptual hurdle, this problem is a plug and chug. Take the values that you have, multiply them all out. The answer to this problem is 3.6 times 10 to the 4th joules. Part B. Calculate the heat produced by an electric iron which has a resistance of 30 ohms and takes a current of 3 amperes when it is switched on for 15 seconds. So you're given that amount of time. And this question, calculate the amount of heat energy. So we're going to, again, be using several of these expressions, rearranging them, okay? Recall that power is equal to the current squared multiplied by the resistance. We get that one by taking the power equation and taking current and voltage and taking Ohm's law. Well, voltage is equal to current times resistance, rearranging one in terms of the known variables, plugging it in to the other one, and solving for the unknown variable. And so you need to make sure you read those preceding facts on the problem set. All right, so once we get through this conceptual hurdle, we are given everything we need. We know the current, we know the resistance, we know the time. This is a plug and chug. Please don't forget to square the current. And we get 4,050 joules as the heat energy produced by this iron. Question 22. A potential drop of 50 volts is measured across a 250 ohm resistor. What is the power developed in the resistor? Now again, this is an application that will allow you to distinguish between when you're solving for the overall energy in joules versus when you're solving for the power or the rate of expenditure, the rate of electrical work. So power is equal to current multiplied by the voltage, and voltage is equal to the current multiplied by the resistance. That's Ohm's law. And so we can rearrange this in terms of another, take both of these, rearrange them. So therefore the current is equal to the voltage divided by resistance. And let's go ahead and plug that in right here. So current is equal to voltage divided by resistance. We got that from algebraically rearranging Ohm's law. And so now I'm going to plug that in right there for current, which is why power is equal to voltage squared divided by the resistance. Once you get past that, this is a plug and chug. You take 50 volts, please don't forget to square it, and divide by the given resistance of 250 ohms, and you will get a value of 10 watts for the power developed by this resistor. Question 23 is an application of some of the preceding facts before this question. A 3 ohm resistor and a 6 ohm resistor are connected in series in an electric circuit. The current through the 3 ohm resistor is found to be 4 amperes. What is the potential difference across the 6 ohm resistor? This question is asking you to solve for the voltage across the 6 ohm resistor. If we were to draw a simple schematic with a battery or a cell and 2 resistors in series, and also write down what we were given in the problem, we have both of our resistors. We also have the current through the 3 ohm resistor. We know Ohm's law is equal to the voltage, rather, is equal to the current multiplied by the resistance. And if we go back and look at some of the facts preceding this question, series resistors are going to carry and have the same current. And that current is going to be equal to whatever the current is through the series combination. Well, all we have here are 2 resistors in series. So the fact that you're given the current through the 3 ohm resistor means you also have the current through the 6 ohm resistor. If you know the current and the resistance for that particular element of the circuit, you have everything you need to solve for the potential difference, i.e. the voltage drop that will occur across. This is something called a VERP table, and depending where we are in class, you may or may not have used a VERP table yet, but it's a very convenient way to organize information about electrical circuits. And so the top row we have voltage, current, resistance, and power. And on the far left column here, we have R1, R2, which is the resistor 1, resistor 2, and then the total column, where you're going to have your totals for voltage, current, resistance, and power. So let's organize what we know. We are given the resistors as 3 and 6 ohms respectively. We've gone through the intuition behind the idea that the current throughout this entire circuit is going to be 4.0 amps. So now what we need to do is go ahead and use the fact that the voltage across series resistors, it can and will be different. However, it's additive. So you can simply go through for a series circuit and add those potential differences to get the total voltage drop across the circuit. So using Ohm's law, you can easily solve for the potential differences for resistor 1 to be 12, resistor 2 to be 24, and using the fact that we're going to add these across this series combination, 24 plus 12 gives you 36 volts for the potential difference for the entire circuit. And specifically to answer this question, across the 6 ohm resistor, we have a 24 volt potential difference there. All right, question 24. The diagram below represents currents in a segment of an electrical circuit. What is the reading on the ammeter? This is an application of Kirchhoff's junction rule. In other words, it is an application of the conservation of charge. What's going into this junction must leave this junction. So let's take a look at our circuit here. And we can see that we have 3 different currents going in. We have 3 going out. However, we have an ammeter that is placed, and this question is asking you, what is the reading on this ammeter? So all we really need to do is apply Kirchhoff's junction rule and look at this and say, well, how much current is exiting? Well, we have 4 plus 1 plus 2 exiting. How much is going in? 3 plus 2 plus, well, whatever it is must add up to 7. That means that it must be 2 amps. All right, so 2 plus 2 plus 3 is 7. That's how many amps go in, and 7 amps go out. Question 25, we have an electrical circuit diagram with locations of an ammeter and a voltmeter, and they're indicated 1, 2, 3, 4. Where should an ammeter be placed to correctly measure the total current, and where should a voltmeter be placed to measure the potential difference? Okay, so let's look at what we have going on here. We have a couple facts preceding this question dealing with the placement of an ammeter and a voltmeter, and you have learned that an ammeter must be inserted into the circuit in series, whereas voltmeters, you're measuring the potential difference across a given element. So you hook a voltmeter in parallel and an ammeter in series. Okay, so let's look at location number 1, which is the correct location for the total current. All right, if we were to track the current leaving this particular circuit, it would head around this way to a junction. It would split, going either this path or this path, because this is a parallel combination here. And then the current would join back together here per conservation of charge and Kirchhoff's junction rule. And all of the current that went in here would be present at location number 1. Location number 2 doesn't work because that's where the current splits. So that's only a portion of the total current. Now let's look at locations 3 and 4 for measuring the potential difference. Location 4, we're going across the battery. That will give you the total potential difference or voltage. And you know that in a parallel combination, the voltage drops across that combination are the same. Okay? So therefore, since there's no other elements, there's no additional loads on this circuit, we just have these two resistors and they are in parallel, then the total potential difference that is across here is the total. These are the same, and therefore they are equal to 4. So locations 3 and 4 would both give you the potential difference. And notice how they are in parallel. They are across an element. One is across the resistor, one is across the battery. And also to reiterate, location 2 doesn't work for an ammeter because it's not going to give you the total current, because we have some current going this way and some going this way, depending on what the values for these resistors, which we are not given in this problem. Question 26. Create a VERP table for the following series circuit. So let's take a look at this circuit. This circuit has a 12 volt overall total potential difference or voltage, and it has 3 resistors, and those 3 resistors are in series. Next, we're going to lay out the VERP table. We're going to have the 3 resistors, our 1, 2, 3, and our total values across that row for voltage, current, resistance, and power. Please note, on occasion, we'll be using kiloohms for resistance and milliamps for current, so please be aware of that. Next, write down the givens. Well, in this problem, we're given the total voltage of 12 and the value for the 3 resistors that are in series. And because they are in series, we can apply some of the preceding facts. Specifically, when resistors are in series, to find the total or equivalent resistance of the circuit, we simply add the values of the individual resistors. So 2 plus 2 plus 2 gives us a total value of 6 kiloohms. Okay? Now, anytime on a VERP table you have 2 out of the 4 values, and really dealing with Ohm's law specifically, you have 2 out of the 3 values, go ahead and solve for the unknowns. So here we're able to find the total current and then the total power. Okay, so total current is 12 divided by 6, and that'll give you 2 milliamps. Now, because we know the total current, and because we're able to apply some of the facts, and namely the fact that the current throughout this entire circuit, which is comprised solely of resistors in series, is constant. So we know that in this instance here, the current for each resistor must also be 2 milliamps. And now, because we have, in regards to Ohm's law, we have 2 out of the 3 variables, we can go ahead and calculate the potential difference across each one, which should add up to the total potential difference because these are all in series. And indeed, 4 plus 4 plus 4 equals 12 volts. Now, lastly, we can calculate the power. That's going to become important later on in some of the questions. And you've already been exposed to what power is. my thought on this is go ahead and just calculate it while you can. And then if you're asked anything regarding the energy dissipation or how much energy is used, you can simply analyze the power. Okay, so question 27. We have a circuit represented by this diagram, and you are asked, what is the reading in the voltmeter labeled V? All right, so this one is specifically asking, what is this reading? And note the voltmeter is hooked up parallel and across the 20 ohm resistor. Let's go ahead and get our VERP table laid out, and let's do what we're always going to do with these. We're going to write into the table what we're given. Well, we're given two resistors, and we're also given the total voltage or potential difference for the circuit to be 60 volts. All right. Now, the next step would be to go ahead and look at the total resistance. We can do this because these are in series, and to calculate the equivalent resistance or total resistance of a series circuit, you simply add the individual resistors. In this case, 20 plus 10 gives us 30. Now we have enough to go ahead and calculate the current. All right, so we know that if we take 60 and divide it by 30, we get 2, and 2 amps is the current in this circuit. However, 2 amps is also going to be the current throughout the entire circuit because each of the resistors, in this case there are 2, are hooked up in series, and the amperage across is constant, which then allows us to find the potential difference for the individual resistors. R1, 40 volts, R2 being 20 volts. We are specifically being asked about across the 20. So across the 20, the voltmeter should read 40 volts. Okay, moving on. Question 28. In the circuit diagram below, you have two 4 ohm resistors, and they are connected to a 16 volt battery. What is the rate at which electrical energy is expended in the circuit? Rate, energy. Now, some of the preceding facts, and in class we've talked about this. When you're asked about energy and the rate of energy expenditure, you're being asked about the power. Let's get a VERP table. Here we have our values for the 2 resistors. They are in series. We're given the total voltage to be 16, and because this is asking you to calculate the power, we can then utilize this equation, and you've seen this take on many different forms depending on how it's being derived. In other words, we can take Ohm's law, rearrange it, and insert it into this equation to solve for use the most convenient and efficient method. All right, so here in this case, because they are in series, we can add 4 plus 4 equals 8, because that's how you find the equivalent resistance or total resistance in a circuit comprised solely of resistors in series. We simply add them up, which means now we can calculate the current. 16 divided by 8 is 2, which means we can very easily calculate the power to be 32 watts to be the total power, which is the electrical energy expended. Question 29. A 50 ohm resistor, an unknown resistor R, a 120 volt source, and an ammeter are connected into a complete circuit. The ammeter reads 0.5 amperes. Part A, calculate the equivalent resistance of the circuit. Well, we're going to start with our VERP table. We're going to fill in what we're given. We know the total potential difference to be 120 volts. We have the value for one resistor But we also have an ammeter, and that ammeter is located in such a position where this is going to be the total current for the circuit. And because it's the total current for the circuit, we can then go on and calculate a number of values here, including the total resistance, which is what A is asking for. The equivalent resistance for this circuit and the total resistance for this circuit are synonymous. They are the same thing. So the answer there would be 240 ohms. We can go ahead and calculate the power to be 60 watts as well. And while we're filling out the VERP table, we can acknowledge something we've used in a number of the preceding questions, that the current throughout this circuit is constant and equal to the total current of 0.5 amps. So we'll go ahead and fill that in, which means that we can quite simply finish filling out the VERP table if we would like to get some of our final values, including the resistance of our unknown resistor, because it's additive. And so if to find the equivalent resistance for a circuit in which there are only series resistors in series, we simply add the individual resistances. And because we know the total resistance, we are able to solve for resistor 2 to be equal to 190 ohms. Okay, and that enables us then to calculate the potential difference for R1 and R2 to really complete our VERP table. And lastly, we're able to find the power dissipated by R, which would be R2, which in this case is 47.5 watts. Question 30. Complete a VERP table for the following circuit. Here's our VERP table. Here we have a circuit, and this circuit has a 12 volt potential difference total, and also has 3 individual resistors, all 3 of which are hooked up in parallel. Let's write down what we know. We know the total voltage, and we know the values in kiloohms of the individual resistors are all 2 kiloohms. Okay, and so now we're going to be applying several facts regarding parallel circuits. So when we're looking at parallel circuits, the voltage drop or potential difference across all the resistors that are in parallel add up to the total. And in this case here, guess what, guys? They're all 12, because the current will either go this way, this way, this way, and regardless of which path is taken, in this case, they're all equivalent. They're all the same, 2 kiloohms. The total voltage will drop across each individual element within this circuit. So that makes it quite simple to find for this particular one, because now we know the voltages for all the resistors. Now, unlike what we saw in a series combination, we cannot simply add up these individual resistances. For any combination in parallel, we need to use this inverse equation, all right, in which the inverse of the equivalent resistance is equal to the summation of the inverse of the individual resistors, all right, R1, R2, R3 in this case. If there were 4 resistors that were in parallel, we would add all 4. If there were 2, we just use 2. But conceptually, what we're doing is we are compressing these 3 resistors into one equivalent resistor. All right, so let's go ahead and find a way to calculate this. Now, the easiest, most efficient way I've found, if the values require a calculator, is to use the inverse button on your calculator. That makes it very simple to solve these problems. Let's put our numbers in here and see what this is going to look like. All right, so here we have a 2, a 2, and a 2, so the inverse of all those added up, but then you need to take the inverse of that, okay? So 1/2 plus 1/2 plus 1/2, but then the inverse of that. All right, and a lot of students forget that. They take the 1/2, 1/2, 1/2, which is the inverse of 2, 2, 2. They add it together, they think they're done, but you're not. You then need to flip it and find the reciprocal or inverse of that. So make sure you're practicing this on your calculator. Make sure you're getting a value of 0.67 kiloohms with 2 significant digits in this case here. And that is the equivalent resistance. Now, what does that mean? What it means is, as I've said already, that it's like you're taking these two individual resistors and you're saying that these two are the equivalent to this one. So if you think about it here on this top one, if we had 1/4 plus 1/4, and we were going to add those, and you get 2/4, but it's the inverse of that, which is equal to 4/2, which is equal to 2 ohms. Okay? That's what I'm saying. Sometimes you don't even need your calculator. But notice that final step there is to find the inverse of that number to get your overall equivalent resistance. Conceptually, I could remove these 3 resistors and replace them with one resistor of 0.67 kiloohms of equivalent resistance, and it would function identically. Okay, now let's finish our verb table here. All right, so rearranging Ohm's law, we are able to get the current is equal to the voltage divided by the resistance. All right, so here we have 12 volts, and we have our total resistance to be 670 ohms. And that will give us a total current of 0.018 amps. Now, that will allow us to really complete this table. Now, notice I'm switching between amps, milliamps, ohms, kiloohms. So you play around with those values a little bit, but what you're going to see here is we're multiplying and dividing by 1,000. So in 1 amp, there are 1,000 milliamps. Therefore, 0.018 amps is equal to 18 milliamps. When given values in kiloohms, it's very convenient to use milliamps and vice versa. And before moving on to question 31, I want to look at a couple things on this verb table. Let's start with the current. So notice that we have a total of 18 milliamps of current, and we have resistors, and they are all the same. So based on our river analogy and the path of least resistance, these are all the same. So we would expect equal amounts of current to go through each of these parallel branches. However, when the current comes back together, when the current splits, so right here, if I had an ammeter at these locations, I would have the total current. Again, that's Kirchhoff's junction rule and an application of the conservation of charge. Now let's look at the resistances. So in a parallel combination, your equivalent or total resistance in that combination of resistors is always going to be less than any individual resistor. All right, so in this case here, we had 3 kiloohm resistors, yet the total or equivalent resistance of this circuit is only 0.67 kiloohms. All right, and that is because the current is splitting across these three different branches. And so those are two things that I wanted to point out that are further affirmation that we've done everything correctly for this particular circuit. Now in question 31, you're asked to draw a diagram for a circuit that has an ideal battery, in other words, a battery with no internal resistance, and two resistors that are hooked up in parallel with each other. And then lastly, an ammeter, and the ammeter needs to be placed in a location to measure the total current of the circuit. All right, so here we have our battery, and we're showing it, that is the source of the potential difference. Then we have two resistors, and they're parallel. So your diagram could be very different, but you need to make sure that when that current comes out and goes this way, that there is a branch where some of the current, call it I1, goes this way, and some of the current, I2, goes the alternate path, and then they will recombine to complete the circuit. And then let's go ahead and put our ammeter in a location that would measure the total current. And so here's one possibility. Here is another possibility. Okay, anywhere between these two, we're going to have the total current. However, as I already indicated, there's going to be a split here. So we're not going to have the total current going through here or here. But when they recombine here, they will be total current, okay? Question 32. Draw a diagram of a circuit that includes a 12-volt electromotive force with a 1.5 ohms of internal resistance and 2 amps of current. The load on this particular circuit has 3 light bulbs. They're all identical. Remember, we're going to treat light bulbs as resistors, and anytime we're asked about brightness, we're going to look at the power to the individual bulbs. Here, all 3 have the same resistance, and so we have 1 bulb that is in series and 2 that are in parallel. You're asked to rank the bulbs on their brightness, in other words, power, and calculate the terminal voltage for the circuit. So, as I've said on the problem sets and in class and in the preceding facts before this problem, that you need to at least be aware of this term in case College Board throws it out there, EMF, electromotive force, which is denoted with a Greek symbol epsilon, E. And that College Board will often use the term ideal battery. Well, when you see that, which we saw a couple questions ago, that's a battery that doesn't have any internal resistance. When in reality, batteries will have this internal resistance. There's a number of factors that would influence the EMF source, including temperature and how much energy has already been dissipated, etc. So here we have a battery, and to the right of that battery, we have a schematic. I want you to be aware of this. We can always go a little above and beyond. So here we see epsilon. And the epsilon, again, is the EMF, or electromotive force. However, within this battery, there's an internal resistance, and that will always be denoted with a lowercase r. Okay, so I've also drawn a schematic to the left over here. It's essentially showing the same thing. I just want you to be aware of it. It's showing a battery that has some sort of internal resistance. So to calculate the potential difference, the voltage of the battery, the terminal voltage, the actual voltage, you're going to need to compensate for that internal resistance using the following formula. So the electromotive force of 12, and then subtract the voltage occurring, that drop occurring because of internal resistance, which would be the current multiplied by the resistance will give you that potential difference. And you'll simply subtract that away from the overall total EMF to get the potential difference or the voltage that is pushing out through the circuit. And in this case, we see the term the load. Those are things that are hooked into the circuit. Those are elements of your circuit. So your load in this case is comprised of 3 identical light bulbs. Now, your schematic could look very different, but please make sure that you are indicating that there's this internal resistance here. And so we have our current that will push out this way. And it's going to, and we're told the current is 2 amps. So here we're going to end up calculating terminal voltage. So we have this 2 amps that pushes out here. And we have 1 light bulb in series. So all the current will go through this light bulb. And then the current will split into 2 and 3. Light bulbs 2 and 3 are in parallel. So this qualifies as a circuit with internal resistance with 3 light bulbs, 1 in series, 2 in parallel. Okay, so labeling everything now, cleaning it up a little bit here. Our EMF 12 volts, internal resistance denoted with a lowercase r, 1.5 ohms. Total current shown on either side of the battery. Now let's do a VERP table and start getting what we know. First, let's find the terminal voltage. So let's go ahead and take our 12 volt EMF and subtract out the potential difference through the internal resistance, which is 2 amps, multiplied by that internal resistance, lowercase r. And so we get a terminal voltage equal to 9 volts. So that's going to be the value that we put in our VERP table. So now we have the total voltage that's going to be pushing through these bulbs, the total potential difference of 9 volts. We have our current to be 2 amps. Now we know the total current is 2 amps. And you're going to treat these like resistors, guys. So we also know that for any series component of a circuit, the current is going to be equal to the total current. Well, that's what's happening here with light bulb 1. So all 2 amps are going to be going through light bulb number 1. That's why I've gone ahead and put 2 amps in for R sub 1, which represents that first light bulb. Okay, then there's some simple ways to solve this problem conceptually. And I'm going to get to that, but bear with me, because as you've heard me say over and over and in class, the more we talk and think about physics, the better and more proficient you will become. And one thing that you know is completely acceptable to do if time permits on the exam is to make up data to help conceptualize, to help utilize that semi-quantitative approach to solving problems. So let's go ahead and say each light bulb has a resistance of 3 ohms. All right. So let's actually fill out a VERP table and do some calculations, even though there's a very simple way to rank the brightnesses of these light bulbs. All right, so resistance is 3, 3, 3. Now, what that enables us to do is to continue on and calculate the potential difference across the first light bulb. So 2 multiplied by 3 equals 6 volts. Okay, so we've dropped 6 of our 9 volts. Now the current will push through a parallel combination. So the current will split, and the resistances between the 2 and the 3 are identical. so equal amounts will go. But we know the same voltage drop will occur across 2 as 3. If we put a voltmeter across 2 and then a voltmeter across 3, they should have identical voltages. And those voltages would be equal to 3 volts. Notice 6 plus 3 is 9, and that gives me my total voltage. And that's Kirchhoff's loop rule, all right, which is nothing more than an application of the conservation of energy. All right, so now we can start to fill this out and calculate the equivalent resistance for the parallel combination, which is the 1 over 3 plus 1 over 3, and the inverse of that. And that's going to give us an equivalent resistance of 1.5 ohms. Notice the subscript usage here. Capital R subscript 23 is saying that is the equivalent resistance for that parallel branch. In other words, I could remove light bulbs 2 and 3 and put a light bulb in that had a resistance of 1.5 and it would work the same. All right, that's what that's saying there. Now what we need to do is go ahead and find the total resistance, which means we're going to analyze the equivalent resistance of the parallel component, which we found to be 1.5 ohms. And now we're going to add the resistance for the single light bulb in series. Oftentimes, it is very helpful to redraw part of the circuit, as I've done here, showing that we have our original light bulb, and then now this parallel branch has been replaced with an equivalent resistance denoted 2,3. All right, which means to find the total resistance, now we can add the 1.5, which was the equivalent resistance for the parallel combination, plus the lone light bulb number 1, which had 3 ohms of resistance, and that will give us the total equivalent resistance for the circuit, and it's equal to 4.5 ohms. So now that we have that, we can go ahead and fill in and find the current. As we predicted, the current through bulbs 2 and 3 are identical and equal to 1 ohm, where that branch occurs, and then they come back together to give the 3. So here, current 2 plus 1 is 3. Our total, 1 plus 1 is 2. Our total current is 2, which we saw through the first light bulb, and we see that as the total. However, when there's a split, half the current, or 1 amp, goes one way, half goes the other way, and then they recombine to complete the circuit. So now, let's go ahead and find the power by multiplying the current multiplied by the voltage, and that gives us 1233 and an overall energy dissipation, overall wattage of 18 watts. Okay, now it's super easy to see. You're probably thinking, all right, so bulb 1 is the brightest, and bulbs 2 and 3 are not nearly as bright, but they're equal. And we were able to accomplish this by making up values, and this took a lot of time, but it's time that will help you overall in this course. It'll make you more efficient later on, having spent this time looking at this. Now for the easy way. All right, so we know power is equal to current multiplied by voltage, and we know Ohm's law, and we also know that you can rearrange Ohm's law and insert it to solve for power and all kinds of different things, really, about electrical circuits. So let's go ahead and take IR and substitute it in for the voltage and get this simple expression that we've talked about in class, where power is equal to the current squared multiplied by the voltage, or the resistance. Now, this may not come to you readily, but if you do this way, it's very simple. So what I'm going to encourage you to do throughout this unit is anytime you have these types of questions, consider the various permutations and rearrangements that you can have for these equations that will enable you to solve questions not only efficiently, but quite simply. So let's look at our ranking is 1 is greater than 2, but 2 is equal to 3. And guys, look at the current going through bulb 1. Look at that current. It's twice the current. And look at what we're doing to that variable in this expression here. We're squaring it. All right. And look at resistance. Resistance is constant for all three. But current is increasing and it's squared. So simply by saying, oh my goodness, bulb 1 has twice the current, and that current, which is 2 amps, is squared and multiplied by the same resistance as all the other ones, we're going to get a much greater value in this case. In question 33, we have a 3 ohm resistor, an unknown resistor, and 2 ammeters that are connected to a 12 volt source. You're given the reading for ammeter 2 as 5 amperes, and you're asked several questions about this circuit. Let's start with A. Find the equivalent resistance for the circuit. Let's start with our VERP table as we normally would and put in what we know. So we know the potential difference total to be 12 volts. We know that voltage drop will be the same across both resistors. There are only 2 resistors and they are in parallel, so I can put 12 volts and 12 volts for resistors 1 and 2. We are given the resistance of resistor 1 here, and then we have a location of amperage at A2 to be 5 amps. So at this given location, that's going to be the total current for the circuit. All right, so we can go ahead and say 5 amps to be the total current for the circuit. So we actually know quite a bit about this circuit. And because we know the total voltage and we know the total current, we can calculate using Ohm's law the total resistance. And the total resistance is the equivalent resistance. So let's answer A to be 2.4. All right, so 12 divided by 5 is equal to 2.4. That is the equivalent resistance. Furthermore, as I've asked you to do repeatedly as needed, you can redraw the circuit because this is the same thing as removing resistor 1 and resistor 2 and replacing it with one resistor of resistance 2.4 ohms. All right, so now that we've done that, let's look at resistor 1 because we can use Ohm's law to find the current. All right, so 12 divided by 3 gives us a current through this branch with the 3 ohm resistor of 4 amperes. So that's how much goes this way. And if we had this here, if we have 4 going this way and we had 5 going in, how much goes this way? Again, an application of Kirchhoff's junction rule, an application of the conservation of charge. This must be 1 amp going that way, and you can either do this conceptually using your knowledge of circuits, or mathematically, if you would like, you can do this as well. And that means our resistance would be 12 for that unknown resistor. Now in question 34, we have a 15 ohm resistor, R1, a 30 ohm resistor, R2, and they're going to be connected. And we want to connect them across points A and B. So you're asked to draw this into the diagram to show these 2 resistors in parallel, and then to determine the potential differences across resistor 1, and lastly calculate the current in resistor 1. So we're just going to do what we've been doing, and we're going to fill out a VERP table because it's great to practice analyzing these circuits. So first things first, let's go ahead and draw these in parallel. So here I have R1, 15 ohms, R2, 30 ohms, and the current has a choice. It can branch across there. That's the key. That no matter how convoluted these get, that's what you need to ask yourself. At that junction, will the current split? If the answer is yes, then you're dealing with parallel components there. All right. Next, we're going to calculate the equivalent resistance. In this case here, we only have these two resistors. So we're going to find the inverse of 15 plus the inverse of 30, and that quantity will take the inverse to find the equivalent resistance, which is the total resistance. Also note, our potential difference is 90 volts for the entire circuit. That is our power, our battery. Our EMF is 90 volts, and therefore across each branch we will drop 90 volts. And that's Kirchhoff's Kirchhoff's loop rule, which is the conservation of energy. All right, so notice the use of subscripts 1 and 2, so that is denoting the resistance for 1 and 2. In this case here, we only have the two resistors, but in more complex circuits, it's important to make sure you're denoting all these resistances, so when you recombine things and go to answer questions, you don't get any of these values mixed up or confused, okay? So 1 over 15 plus 1 over 30, the inverse of that is 10 ohms. So now we can put 10 ohms into our VERP table. If needed, we can show that, hey, if we took both R1 and R2 out of the circuit and replaced it with one resistor, a 10 ohm resistor, that's the equivalent for these two in parallel, okay? All right, so that means we have everything we need to go ahead and calculate the current. 90 divided by 15 is 6, 90 divided by 30 is 3, and a cursory look at our VERP table, everything adds up. Everything makes sense, including our current, which splits 6 amps one way, 3 amps the other, but they recombine for the total current to be 9 amps. And our resistances, we see our equivalent resistance is less than any of the individual resistors in a parallel combination. Again, affirming that we've done things right. And we have our power calculated as well. So from this VERP table, you can answer questions parts B and C, potential difference 90 volts, and current through resistor 2 to be 6 amps. All right, question 35 here. We have a 20 ohm resistor and a 30 ohm resistor. They're connected in parallel to a 12 volt battery. We are given a schematic here. We're also shown an ammeter that's located within the circuit. What is the equivalent resistance of the circuit? In other words, what is the total resistance of the circuit? B, what is the current reading at the ammeter? Well, we see it's at a split. All right, so immediately we know that that current reading in that given location is less than the total current for the circuit. Lastly, what is the power of the 30 ohm resistor? So we have our VERP table. Let's go ahead and fill it out. We have a 12 volt battery, and we have two resistors in parallel, which means the potential difference across each resistor is going to be all 12 volts, and we are given the values for the resistances, which means that we're able to go ahead and calculate the equivalent resistance. In other words, we're going to find what the resistance of the 20 and 30 ohm resistors are in parallel using this relationship 1 over 20 plus 1 over 30, and the inverse of that will give you the equivalent resistance of 12 ohms. Note 12 ohms is less than 20 and less than 30. So that means that you're doing things correctly, because the equivalent resistance for resistors in parallel is going to be less than any value of an individual resistor when hooked up in parallel. If needed, you can redraw the diagram to show the two resistors being replaced with one equivalent resistor of 12 ohms. So looking at the VERP table, you can now put 12 ohms as the total resistance, which means you can calculate the current for the entire circuit to be 12 divided by 12, or 1, which then means you can go through and find the individual currents, because we know the voltage and we know the resistance. Using Ohm's law, we can find resistance 1, current 1 to be 0.6 amps, current 2 to be 0.4 amps. Lastly, we can use any equations we'd like to solve for power. Typically, we'll use current multiplied by voltage to get 7.2, 4.8, and 12. And specifically to answer part C of 4.8 watts would be the rate of energy dissipation across that one element in the circuit. Question 36. Find the current through R2 in the circuit below. All right, so we have 4 different resistors going on here. We have 2 in series and we have 2 in parallel. Here's our VERP table. We're going to write down what we know. We know the value for all 4 resistors. We also know we're dealing here with a 10-volt EMF or battery, and so we know the total voltage or potential difference for this circuit. So, first things first, compress those 2 resistors that are in parallel and find the equivalent resistance for the parallel component of the circuit. So 1 over 30 plus 1 over 50, the reciprocal or the inverse of that will give you the equivalent resistance for resistors 2, 3. Again, note the use of the subscripts here. That is telling me this is the equivalent resistance for resistors 2 and 3 only. It does not include 1 and 4. 1 and 4 are in series, whereas 2 and 3 were in parallel. So now that I know the equivalent resistance for 2, 3, I can simply add up the individual resistances for 1 and 4 because they're in series. Remember, we can add those. We can redraw the circuit to help conceptualize the problem and say, wait a minute, okay, now that we have the equivalent resistance 2, 3, I can redraw it, and now it becomes very simple to see. I'm going to add 20 plus 18.75 plus 20 to get a total resistance for this circuit of 58.75. Now look at the parallel component again, please. The parallel equivalent was 18.75. That is less than 30. That is less than 50. So that value makes sense for that portion of the circuit. Now we have enough information where we can find the total current. So 10 divided by 58.75 is equal to 0.17. Once you get 0.17 here, then you need to pause and say, wait a minute, I have 2 resistors in series. All the current will go through there. All of the currents going through here, and all of the currents going through there. So I'm going to go ahead and fill those portions of the VERP table out as well. Resistors 1 and 4 will have 0.17 amps going through them. That enables me to use Ohm's law to calculate the potential difference. R1 equals 3.4, R4 equals 3.4 because they have the same resistance and the same amount of current going through them. So those numbers make sense. The next step is going to be figuring out what's going on across the R2 and R3. All right. We know our total potential difference is 10 volts. We know we have 3.4 plus 3.4 or 6.8 volts being dropped across resistors 1 and 4. That leaves a total voltage for the parallel components of 3.2 volts. Again, 3.4 plus 3.4 is equal to 6.8. 10 minus 6.8 is 3.2. And 3.2 is the potential difference not only across R2, but across R3 as well. And so when we look at these values here, these are the two that are in parallel. But when we add this and this, we get 10, and that means that energy's been conserved. Again, that's an application of Kirchhoff's loop rule, conservation of energy. And now we can go ahead and complete the verb table and find the current that's going through R2 to be 0.107 amps. We can also go ahead and calculate power, and that really is about everything we can do with this circuit, and we've addressed the question about the current in R2. But again, doing a verb table for the entire problem, it's only going to make you more proficient at solving circuit problems. On the AP exam, you don't have time for all that, but you will use verb tables to find pieces of information that may not be readily apparent. Then you can stop and move on. Here, as we're practicing, we're finishing and completing out the entire verb table for all of these problems. For question 30, we have 4 different circuits we're analyzing, and we're ranking the current through R2, energy dissipated by R1, the equivalent resistance for the entire circuit, and lastly, the potential drop across R2. Now, to get as much practice as possible, we're going to do verb tables for all 4 of these circuits, and then that'll make our ranking task much easier. Let's get started with circuit A. Fill in what we know from the verb table. We know the resistance for R1, R2. We also know the total voltage for the circuit. Now, using your knowledge of a series circuit, you know that you can add the individual resistances. So 10 plus 10 would give the total resistance for the circuit of 20 ohms. We can now apply Ohm's law. 10 divided by 20 is 0.5 amps. Next, because this is a series circuit, the current through the circuit will remain constant. So if we know the total current to be 0.5, we know the current through R1 and R2 to also be 0.5. Using Ohm's law, we can calculate the voltage for R1 to be 5, R2 to also be 5, and using Kirchhoff's loop rule, we can look and say, okay, in the loop rule, energy is conserved, and we can simply add the voltage drops across R1 and across R2, and the sum of those will equal 10 for the total volts across the circuit. Lastly, you can calculate the power by taking the current multiplied by the voltage and get these values. Let's look at B. For B, we have 1 resistor in series, and we have R2 and R3 in parallel. Your verb table for circuit B, you know the identity of all 3 resistors. You also know the total potential difference for the circuit to be 10 volts. Next, calculate the equivalent resistance for the parallel combination. 1 divided by 10 plus 1 divided by 10. Take the inverse of that, and you will get an equivalent resistance of 5 ohms. Note the use of subscripts 2, 3 to denote that this is referring to the resistance across resistors 2 and 3 only. To find the total resistance for the circuit, we would then need to add R1. And by adding R1 to the equivalent resistance of 2, 3, you can get a total resistance or total equivalent resistance of 15 ohms for this circuit. Please note, for the equivalent resistance 2, 3, that value of 5 ohms is less than both values, and therefore that's further affirmation that you're doing this correctly. Using Ohm's law, we can calculate the current 10 divided by 15 is 0.67 amps. Then we know if that's the total current through the circuit, it must also be the current through R1. So if it's the current through R1, then we use Ohm's law to find the potential drop across R1 to be 6.7 volts. Next, we can look at how many total volts we have. We have 10. How many dropped? 6.7. 10 minus 6.7 leaves us 3.3. Therefore, we know that the remaining voltage drops, which will be the same across R1 and R2, will be 3.3 volts. Then, using Ohm's law, we can solve for the current at this parallel combination. They should be the same, as the resistances are the same and the voltage drops are the same. Therefore, the current should be the same, and the current should add to the total current. And indeed, it does add to 0.67 with two significant figures. Lastly, you can calculate power by taking the current multiplied by the voltage. Let's move on to circuit C. Circuit C, we have two resistors. They are in parallel. Our VERP table, we know the identity of the two resistors. We also know that the potential difference is 10 volts, and thus will be 10 volts across R1 and across R2, which means that we can now calculate the equivalent resistance for the overall circuit by adding the inverse of 10 and then taking the inverse of that answer to get an equivalent resistance of 5 ohms. Note the use of subscripts 1, 2 to denote the resistors 1 and 2. Even though those are the only resistors in this particular circuit, it's important to be consistent with that for more complex problems. If the equivalent resistance of 1, 2 is 5 ohms, then the entire resistance of the circuit is also 5 ohms. And now we can use the fact that we know total voltage and total resistance to calculate total current as 2 amps. That's Ohm's law. 10 divided by 5 is 2. Next, we can simply say, well, the resistance of each path is the same. So we would expect half the current to go through R1, half the current to go through R2. So each of these resistors will have 1 ampere of current moving through it, which combines to the total current, Kirchhoff's junction rule, and conservation of charge of 2 amps. Lastly, you can calculate power by taking the voltage multiplied by the current, and we can move on to circuit D. We know the value for all 4 of the resistors is 10 ohms. We also know the current, the total voltage to be 20 volts. So that means we can go ahead and calculate the equivalent resistance. You see a pattern here, I hope, for figuring these problems out. 1 divided by 10 plus 1 divided by 10, the inverse of that, as we know, gives an equivalent resistance for resistors 2, 3 of 5 ohms. Now, we have 2 other resistors. However, those resistors are in series. So R1 and 4 are in series, whereas R2 and 3 are a parallel combination. So now that we found the 2, 3 equivalent resistance, we can add that to resistor 1 and resistor 4 to get an overall total equivalent resistance of 25 ohms. Next, you can use Ohm's law. 20 divided by 25 is equal to 0.8 amps. That's the total current. Well, if the total current is 0.8 amps, then we also know something about resistor 1 and resistor 4 are also going to be 0.8 amps, as that will remain constant and the same as the total current in a circuit. Next, we can use the Ohm's law to calculate the potential difference across R1 and R4 to both be 8 volts. We know that's additive, so that's 8 plus 8. We've dropped 16 volts across R1 and R2. We can also acknowledge the fact that our remaining current is going to split. So our 0.8 splits, half goes through R2, half goes through R1, that's 0.4 and 0.4, which again, we can use Ohm's law here to calculate the potential difference. Another way to find the potential difference would be to say, if we've lost 8 here, that's 16, and 20 minus 16 is equal to 4, and these are in parallel, so we're going to drop 4 volts across each one, and that will add overall to 20, so that way works as well. Lastly, you can calculate the power by taking the voltage multiplied by the current, and we can finally move on to the ranking task. Here are the 4 circuits together. Here are the 4 VERP tables that you can take a look at and rank. I'm going to go quickly through this because we've already gone through each circuit individually. So ranking the current through R2, you're going to get from highest to lowest CADB. For looking at energy dissipated through R1, remember you're going to look at the power. That's what the energy dissipated is asking for, is the power. Highest to lowest, CDBA. And for the equivalent resistance or the total resistance for the circuit, you're going to get from highest to lowest, DABC. And lastly, the potential drop or potential difference across R2 from highest to lowest, CADB. Question 38. For the remaining questions on the problem set, we're going to simply be creating and filling out VERP tables. So let's get started with 38 here. We have 4 resistors. All 4 of them are hooked up in parallel. So to start off our VERP table, you'll put the identities of all 4 resistors, and you also know the total potential difference to be 12 volts. Now, as you've been doing throughout the problem set, the next step is going to be to say, all right, is this a purely series circuit? Is it a purely parallel? Or is it a combination of series and parallel components? And that's going to determine your next steps on the VERP table. Here, since it's purely parallel, you can go ahead and put the potential difference for R1, 2, 3, and 4 to all be 12 volts. Next, you'll go ahead and calculate the overall equivalent resistance for these 4 resistors by taking the inverse of the individual resistors, adding those together, and taking the inverse of that value. That's going to give you a equivalent resistance, and in this case, a total resistance of 3.0 ohms. Please note, 3.0 ohms is less than any individual resistor in this parallel circuit, which is further affirmation that you're doing the problem correctly. Now we know the resistance total and we know the voltage total, which means Ohm's law can be applied to calculate the total current. 12 divided by 3 is equal to 4 amps. Now that we know that, we can apply that information to the remainder of the circuit. If we know the total amps or total current through here to be 4, then you can start calculating all the other currents because you have 2 out of the 3 values for Ohm's law. You have total voltage. You got that because you understood, hopefully, that it's all parallel. So it's 12, 12, 12, 12. And we know the resistors. So we could have just right off the bat calculated the individual currents and then added them all together. And they should all equal up to 4. Something else to make note of. Resistor 1 has the greatest current through it. Well, resistor 1 also has the lowest resistance, and therefore it would make sense that the lowest resistance has the highest current due to that inverse relationship. Hey, come say hi to my students. And now that we have all of this information, we can go ahead and calculate the power by taking the current, multiplying it by the voltage. You should see all of these add up to the total power of 48 watts. Question 39, we have a circuit here. Let's get a verb table going, and we know the value of the three resistors. They are all in parallel. The total potential difference is 12 volts, and because they're all in parallel, the voltage drop across each individual resistor will also be 12 volts. This means that our next step could be calculating the equivalent resistance. Again, you see a pattern here. The 1 over 30 plus 1 over 20 plus 1 over 10, and the inverse of that will give you the equivalent resistance, in this case for the entire circuit, to be 5.45 ohms. Please note that 5.45 ohms is less than the resistance of any of the individual resistors, which is further affirmation that you're doing these problems correctly. Next step, using Ohm's Law to fill out the table, and we have enough information to calculate all of the currents and all of the powers based on the fact that we were able to identify it as parallel, identify those potential differences, find that equivalent total resistance, and then the rest was very straightforward. In the next problem, we have a circuit in which we have one resistor in series and two resistors in parallel, and together they make up the entire circuit. Let's get a verb table started. We have the values for all three resistors. These values are in kiloohms, which means we'll use milliamps to express the current, although you don't have to do that. That's totally up to you. We also know the voltage here. The total voltage is 10 volts. So our next steps are going to be to calculate the equivalent resistance for the parallel combination, 1 over 8 plus 1 over 10. The inverse of that quantity will give you an equivalent resistance of 4.4 kiloohms. Note the use of subscripts 2, 3 to denote that this is the equivalent resistance across or for resistors 2 and 3. So we still need to include resistor 1 for the total equivalent resistance of the circuit. That next step is fairly straightforward. We can simply add the equivalent resistance for the parallel combination to 2 kiloohms, which is the series resistor, to get our total resistance. Recall, it's very helpful to redraw the circuit to help you to conceptualize it. So this is the equivalent of taking the 8 and 10 kiloohm resistor, taking them out and replacing those two with one resistor that is 4.4 kiloohms. And now you can see you have two resistors in series, so you simply add 2 plus 4.4 to get a total resistance for the circuit. Next, 10 divided by 6.4 gives you 1.6 milliamps. That's the total current in this circuit. The next step here would be to use that information and say to yourself, okay, if 1.6 is the total current, then it's also the same amount of current going through this series resistor here, because that is going to be constant for any series component. So you can get that put into the verb table, which means we can now calculate the potential difference across R1. And that's going to be equal to 1.6 times 2, or 3.2 volts. Now the next step would be to say, all right, so the voltage across 2 and 3 must be equal to the total potential difference, 10, minus the drop across R1, which was 3.2 volts, and that gives you 6.8 volts. And then the voltage drop across these parallel combinations are both going to be 6.8. So coming to that realization makes the rest of this verb table very simple to fill out. Application here of Ohm's Law will give you all of the currents going through. It's important for you to please always stop and think about, okay, when the current splits, when they come together, do they equal the total current? In other words, 0.9 amps plus 0.7 amps equals 1.6 amps. That makes sense. Do my voltages add up? Am I compensating or looking at the drops across parallel components and looking at those separately from series components? 3.2 plus 6.8 gives me my 10, and that is Kirchhoff's loop rule, which is an application of the conservation of energy. Next, you can calculate the power dissipated by the individual components along with the total power dissipated by the circuit, and that'll give you a complete VERP table. Question 41, we have a circuit in which we have an unknown potential difference, an unknown total voltage. Then we have one resistor that is in series and two resistors that are in parallel, and we're given the current through a section of one of the parallel components. Let's get a VERP table going for this one. We know all three resistors, we know the value, and we also know that we have a 21 milliamp current at this exact location. Well, application of Kirchhoff's junction rule and conservation of charge, whatever the total charge is that you have, you're going to have some going this way and some going through the 70 ohm resistor. You're going to have more going through this branch, the 70, because it has a smaller resistance. And that's the inverse relationship that is current and resistance. So this amount here represents the current that went through R2, which is our 100 ohm resistor. So we have that information. The next step in this problem is to calculate the voltage drop for R2. Remember, guys, when we have 2 out of 3, we can use Ohm's Law. And indeed, you really need to do that. Anytime you get enough to do a computation, go ahead and do it, because oftentimes it'll elucidate that next step of where you're going. Because the most common thing I hear students say is they get to a point on the VERP table, and then they're not sure where to go next. All right, so R2, if that has a potential drop of 2.1, then R3 also has a 2.1 voltage drop. Remember, they're in parallel. So the potential difference or voltage drop across each one will be the same. Then we can go ahead and calculate the current through R3. So R3 is 0.03. So as we predicted, it has more current than R2. So our prediction holds true based on this computation. Then we can say, well, that's the total current. When R2 and R3 come together, this is the total current. So now we know the current for the whole circuit to be 0.051 amps, which means we can go up and put it for resistor 1. Because resistor 1 is in series, and the current in a series combination will remain constant. And in this case, it's total to the current, total current through this particular circuit. Now we can apply Ohm's Law, and we can calculate resistance 1 to be 2.55 volts. Lastly, we can then look at the equivalent resistance of 2,3, which would be 1 divided by 100 plus 1 divided by 70, and the inverse of that gives us a equivalent resistance for the parallel combination of 41 ohms. Note the use of subscripts 2 and 3 to denote that this is the resistance across resistors 2 and 3. We still need to add 50 ohms to this. 41 plus 50 gives a total resistance of 91 ohms. Ohm's Law allows us to calculate all of these values, and we know the total voltage as well, because we can get that a couple different ways. We can get it by saying 2.1 plus 2.55, that's the total voltage or potential difference, which is equal to 4.65. So you could use that approach, or you could use an Ohm's Law computation as well. All right, so it's interesting to also look at this way to calculate. Again, once you get to this stage in your VERP table and your circuit analysis, there's a number of different ways. So use whatever is intuitive to you, but also make sure you double.
Guys are on their way.
Thank you for letting me know. But also make sure you go back and look at your VERP table and all of our different rules and things that you know about parallel and series and Kirchhoff's junction, Kirchhoff's loop. All of those make sense. That's important, and everything adds up to be approximately correct. Remember, we're not going to stress out over, minor discrepancies in these calculations. But as long as they're close, you're going to be in good shape here. So we were able to also calculate the total voltage by using Ohm's law, because we knew the total current and we knew the total resistance. So that could also be another way to get 4.65, and they match. And so you can be confident when that happens that you've got everything correct. Now we can calculate power by taking current multiplied by voltage. They should all add up to be 0.24 watts. And indeed, that's exactly how they add up. Okay, question 42. We have a very interesting circuit. This one is a little different. So it's important for this one for you to look at where the current's going. So current's going this way, which means it will have a junction or a split that will occur. All right, and it's either going to go this way or it's going to go this way. And you could predict the resistor with the higher resistance, the 1.4, will have less current than the 1.2. That's just that initial analysis before you start a problem. Then they will come together, the current, that is, will come together, and whatever the total current is, it will then split again. All right, so a little intuition before just starting out a problem, because at first you might be tempted to put all of these in parallel and analyze them as the equivalent resistance of the inverses of all four resistors, and that would be incorrect. Let's get our VERP table filled out. We know the resistances, we're given those in kiloohms. We also know the total potential difference is 12 volts. We need to find the equivalent resistance across 1 and 2 first. So across 1 and 2, we get 1 divided by 1.2 plus 1 divided by 1.4. The inverse of that gives an equivalent resistance of 0.65 kiloohms. Again, that's only for those top 2 resistors. Next step, we need to do the same thing for R23, which denotes resistors 2 and 3 compressed into one equivalent resistance. And the inverse of those gives us a overall resistance of 0.85 kiloohms. So we have those individual equivalent resistances. Next, my recommendation would be to redraw the circuit to show that now we have 2 resistors. We have R12 and R34 in series. So we can simply add them. And that's going to give us the total resistance for this circuit at 1.5 kiloohms. Now that we know that information, we can use Ohm's law. 12 divided by 1.5 gives us the total current. So we have 8 milliamps of current pushing through this circuit. The next step here is going to be to look at each drop separately. So this is different than some of them we've been working out. So we're going to look at the voltage drop or potential difference across R12. Remember, R12 is this guy right here. Okay, so across R12, we can calculate using Ohm's law. We can get the total potential difference to be 5.2 volts. Now, this is still an equivalent resistor. We haven't expanded it back out into its individual 1.2, 1.4 kilo ohms, but we do know the potential difference is 5.2 volts. And we do know that the potential difference across a parallel combination is the same, which means that we can do this for V34, and using that same line of logic, we are able to fill out our VERP table and say there's a 5.2 potential difference across both R1, R2, then 12 minus 5.2, or using Ohm's law, like we did right here, either way works, we can then get a potential difference of 6.8. So you can either say, okay, 12 minus 5.2 is 6.8, or if you have time and you're really sitting down to think about this, do both ways. As I've explained here, if they support one another, 6.8 and 6.8, then you know that you've done this correctly. Now that we have this information, we can use Ohm's law to calculate the resistance, or excuse me, the current for resistors 1, 2, 3, 4, because the conceptual hurdle is done. All right? The conceptual hurdle was analyzing these two components separately, finding the equivalent resistance, plugging those values in, and then recognizing because the potential difference across 1, 2 and 3, 4 are the same, if we can find one, then we can easily find the difference for the other one. Okay. Lastly, we can calculate the power, and the power should all add up to 0.096 watts. Question 43. So this circuit looks a little different, but let's start by writing down what we know. In the VERP table, we know the resistances for resistors 1, 2, and 3, and we also know the total potential difference. Now, here's what's a little different about this particular circuit, is we have a series combination within a parallel combination. So resistors 1 and 2, what we're going to do is what we would do for any series combination, and that is to add the resistors. In this case, we have a 100 and a 200 ohm resistor, so we're going to add those together for 300 ohms. Then we're going to employ our usual methodology for a parallel combination. In other words, I would recommend that you redraw the circuit and conceptually analyze the circuit, and you can see from the redrawn circuit that now we have a simple parallel circuit here. Next, calculate the equivalent resistance. And doing so, the major misconception here is students will do the 1 over 100 plus 1 over 200 plus. What you need to do is the 1 over 300 plus the 1 over 400, and then take the inverse of that to get the equivalent resistor. Note the use of the subscripts 1, 2, 3, which denotes that this is the equivalent resistance for this entire circuit, which means it is the total resistance for this entire circuit. This can be redrawn once again to show if all three of these resistors were removed and replaced with one resistor of 171 ohms, it would have the same resistance overall for the circuit. Next, we have 2 out of the 3 variables for Ohm's law, so you can easily calculate the total current to be 0.058 amps. Now, we can go through and look at R3. R3 is one branch of this parallel circuit. Now, R3 will drop the full 10 volts across it. So the potential difference for that one resistor is 10 volts. However, we cannot do that for the other branch, which in reality, the other branch has two resistors in series. So with R3, you can go ahead using Ohm's law, and you can 10 divided by 400, you can get 0.025 amps going through that branch, which means the remaining current will go through the branch with the two resistors in series. Okay, so we can say 0.058 minus 0.025, and that gives us 0.033 amps, which is going across that upper branch. Now, the upper branch has two resistors in series, and what do we know about resistors in series with regards to current? Well, we know that the current will be constant. So because we know 0.033 amps will go across those two resistors and remain constant, we've now identified currents for R1, R2, which means we have enough information to calculate the potential difference across each individual resistor, R1 and R2. Also note that R1 resistance, or the potential difference across R1 plus the potential difference across R2 adds up to 10 volts, which is the potential difference for the entire circuit. Now it's very straightforward to go ahead and calculate the power, which will all add up to the total power of 0.58 watts. Question 44, we have a circuit and it's similar to 43, however, we have one additional element, and that would be the 10 ohm resistor. So let's start with our VERP table. We have a total of 4 resistors. What do we know? Well, we know the potential difference for the entire circuit is 12 volts. We also know the resistance for the resistors 1 through 4 to be 2, 5, 6, and 10 ohms respectively. So next, we're going to go ahead and calculate the overall equivalent resistance. You're going to do what we did in question 43. You're going to take the 5 and 6 ohm resistors, which are part of a parallel combination. However, in themselves, in their respective branch, they're in series. So you're going to add 5 plus 6 and take the inverse of 11. Then you're going to add the inverse of 2. And this is going to give us the overall equivalent resistance for the parallel combination. All right. So that resistance for 1, 2, 3 is equal to 1.692 ohms. Now, I do want to preface the remainder of this question and let you know that I have carried out a number of significant digits because in the end, if you're not careful with your rounding with this particular problem, you can end up with some of the voltages not adding up correctly. Very minor differences. However, in this video, I want everything to add up correctly. So again, we're not going to obsess over these small differences. College Board is not going to obsess over small differences. However, in this video, you'll see at the end of this question why I'm carrying out so many digits. It's just so they add up correctly for the video. Okay, so we have our resistance. However, we have one more resistor. and that would be the resistor, the 10 ohm resistor. So what we're going to do is add 1.692, and we're going to add that to 10 to get a total equivalent resistance for the entire circuit of 11.692, around 11.7. Now we can use Ohm's law to calculate the total current to be 1.0263 amperes. Next, we can analyze resistor 4, because now that we know the total current through the circuit, and we know that that total current through the circuit is going to be constant across the 10 ohm resistor, and we also know all of the currents coming out of this branch here. We know some will go here, some will go across the series combination, but it will all end up being here. So if we had an ammeter and wanted to measure total current, you could place an ammeter here, you could place one here or anywhere up here, and you'd get the total current. Okay, so that's why we're able to say the total current for R4 is also 1.0263 amperes. Then we can use Ohm's law to find the potential difference across the 10 ohm resistor. That is 10.263. Next, now that we know that potential difference across there, we can say what's left. Well, the remaining voltage drop is about 1.7 volts. So that's 12 minus 2.3. Again, I'm carrying out more digits so that it adds up perfectly in the end. And by doing so, we now know R1 has a potential difference of 1.737 if you were to subtract 12 minus 10.263. Okay, so that gives us R1 completed, and the remaining step would be to look at the current. If 0.8685 amps flows through the branch with the 2 ohm resistor, which is R1, then the remaining current must flow through R2 and R3. So we can take 1.0263 and subtract 0.8685 to get the current, which will be constant across R2 and R3, to be equal to 0.1578. Now we can use Ohm's law and simply calculate the potential difference for both R2 and R3. And what you'll see is those will add up correctly to give you the total amount, okay? So you'll have a total of 12 volts across the entire circuit. We're going to drop 10 volts across R4, and the remaining voltage will drop with the remaining going across R1 to be 1.737, and then if you are to take R2 plus R3, you'll get the remaining current, and it all adds up to 12 volts. Lastly, you can calculate the power, which will all equal 12.3 watts. Question 45, we have a circuit here, and we're given, at one location, we're given the current flowing through it, and we have a mystery resistor. This is going to be fun. But we're given the voltage drop or potential difference across the mystery resistor. Let's do what we always do. Start with the verb table and start with what we know. So although we don't know the resistance for R1, we do know the potential difference is 3 volts. We also know the total potential difference is 15 volts. We know that we have a total of 4 resistors. We know that we have a parallel branch as well. Next, we want to look at where we're given the current. What's interesting about this particular location is if you put an ammeter here it would give you the total current. So, and same with up here. If you put an ammeter up here, it would give you the total current. Total current. Total current. All right. So 150 milliamps is the total current for the circuit. So we can also put that in our VERP table as 0.15 amps. Okay. So the next step would be to go ahead and calculate the resistance across the entire circuit. We have 2 out of the 3 variables for Ohm's law, so we can take 15 and divide it by 0.15, and we know the overall resistance in this circuit is 100 ohms. All right, so the next step, since we know the total current, we also know the total current going across R1 and R4. So we can go ahead and put 0.15 amps into the VERP table, which means for R1, we have enough information to calculate the resistance because we have 2 out of the 3 variables for Ohm's law. So we can say 3 divided by 0.15 is equal to 20. So our mystery resistor is no longer a mystery. It is 20 ohms. Next, we will calculate the equivalent resistance for the parallel component, just like we've always done. So in this final circuit on this problem set, you're seeing these patterns, and you just keep using these patterns to analyze any circuits that you are given, and you will be successful. So 1 over 100 plus 1 over 200 is going to give us the equivalent resistance. And the inverse of that is going to equal 66.7 ohms. So now we know the equivalent resistance for the parallel combination. Again, note the use of subscripts 2, 3, which denotes that this is the resistance across both resistor 1 or 2 and resistor 3, and that number is equal to 66.7. That's very useful. Now we can redraw the diagram. However, we now know the resistance of the mystery resistor to be 20 ohms. We are given nothing about R4. However, we do know the current based on the current reading in the circuit. All right, so we know the current across R4. So we can find this using Kirchhoff's loop rule, Ohm's law, and of course the equivalent resistance for the circuit. Let's look at what this would look like. We know the potential difference across the entire circuit is 15 volts. We know voltage drop across R1 is 3 volts, and we know the voltage drop across the parallel combination is going to be the product of the current multiplied by the resistance across the parallel combination. All right, that's going to give us the voltage drop across that parallel combination, and then plus the voltage drop across the 4th resistor. All right, so again, this is nothing more than an application of the conservation of energy, and it's known as Kirchhoff's loop rule. So we know the voltage drop across R4 is 2 volts. So we're able to find all of this information out. We now know the potential differences across all of the elements of this circuit, R1 through R4. R4, we're now able, since we know the potential difference is 2 volts, we can now use Ohm's law to go ahead and calculate the resistance of R4 to be 13.3 ohms. Okay, and last, we're able to find the current that goes across R2, R3. Please note, Kirchhoff's junction rule, conservation of charge, that current splits across the parallel combination where you have 0.1 amps going one way and 0.05 amps going another way. But when they recombine, you have your total amperes of 0.15 amps. Also notice that you have 0. much less current going through the branch with the higher resistance, which is that inverse relationship we discussed earlier on the podcast and in this video and on your problem set as well. Let's calculate the power here and go ahead and wrap this up. So the power will all add up to the total power of 2.25 watts, and that completes this VERP table. It also completes this problem set. So I will see you guys in class.